Welcome, everyone. I'm Marcia McNutt, President of the National Academy of Sciences, and it is my distinct pleasure to welcome you to one of the highlights of the National Academy's annual meeting, and that is our plenary symposium, which this year considers grand challenges in science and whether the National Academy of Sciences should initiate a special program to articulate some civilization-shaping grand challenges. Now, why are we doing this? Well, let me tell you my own personal story of why I think a program in grand challenges could be timely and interesting. When I was a young child growing up in Minnesota, I was personally inspired by the space program, by the Mercury and Apollo astronauts. I remember as a fourth grade student getting together with my girlfriends and forming our own astronauts club. We each adopted alternate persona of one of the astronauts. I got to be Gus Grissom, and our little astronauts club plotted our own space launch. We selected the smallest girl in our class, Phoebe Walling, and we decided we were going to launch Phoebe Walling in a trash can as high as we could launch her and have her splash down in Lake of the Isles. Well, it was perhaps not a very well thought out plan, but when I look back at our little astronauts club many years later, I realized that each of us girls in the astronauts club eventually either became a scientist, a doctor, or went into a technical field. So although none of us went to space, and none of us actually became in any way a space scientist, all of us were inspired by Kennedy's vision that we should go to the moon, not because it was easy, but because it was hard. And that caused us to want to learn about science and study science and eventually put it towards all different directions of public good. So if I could have my first slide, please. I think there are, yes. Okay, so why else, other than my own personal astronauts club, why would we put forward grand challenges? Well, I think one reason is it's human nature. I believe humans rise to our greatest achievements when we are challenged by the seemingly impossible. If we put forward low bars, we only rise to the very insignificant. But if we put forward very high bars, then we rise to our greatest heights as human beings. The second is to provide inspiration, as it was for me, for the very best and brightest young Americans to pursue careers in science. There's no reason why young people shouldn't also go into business or become actors or basketball players. But right now, when we look at how we've been providing the talent in technical fields for America, we have been counting on foreign talent to supply our domestic need. It has been the best and brightest coming from all over the world to fill our universities and our companies and our universities, faculty, and also our government labs. Now they have just as good opportunities back home. They are not going to be coming here in the same numbers. So we have to grow our own talent. And finally, a third reason that I'll put forward is maybe just to motivate change. Grand challenges can change the way in how we educate people, change in what we decide to value, in the partnerships we pursue, and perhaps how we even operate as an academy. There could be many reasons why we would want to motivate change and use the grand challenges to do it. So if I could have the next slide. I want to set expectations appropriate for this symposium in what I hope we can accomplish with it and what I don't want the purposes of today to be. First of all, I want to gauge interest from all the members of the Academy in pursuing a Grand Challenge program. But the purpose of today is not to select specific topics for a Grand Challenge program. So I don't want to be seeing emails from all of you saying, "Dear Marcia, I thought idea number 2 was really not worthy of a Grand Challenge," or "I thought idea 4 should be tweaked in this way." Don't do that. We are not selecting Grand Challenges today. I also hope we'll hear about possible benefits that might accrue from such a program and pitfalls to avoid from those who have gone before us. But we are not going to today decide on what the goals for a National Academy of Sciences program might be and what the metrics are for success. That will come much later. We're just going to get inspiration from programs that have come before and some guidance from them. We are not going to decide on our own program today. And third, we're going to explore potential implications or impact on the culture and practice of science or on science education from those who have gone before. We are not today going to design program elements or execution. So no details today. All we're getting is some ideas and some inspiration. So finally, if we could go to my last slide. If you have thoughts and reactions, please feel free to write to naspresident@nas.edu. Particularly, write me if you have, say, $1 million and you say, "I love the idea of a Grand Challenges program, and here's a check to support a committee to look in more detail at this, or to hire some staff who might want to help put together something. Or if you really want to help with it, or if you think this is a rotten idea, write me. But don't try to fine-tune anything at this point." So with that introduction, I would like to introduce the session chair of our first panel. It is the very distinguished Victor Zhao, who will moderate panel 1, and he's going to be giving views from other initiatives which have gone before, and he will introduce his speakers, but I'm sure this will be a lively panel with a variety of different initiatives that have operated in some very unique ways. So Victor, and of course, Victor is the president of the National Academy of Engineering and National Academy of Medicine. I do that all the time. National Academy of Medicine. Many of you perhaps heard the great panel he did yesterday on COVID-19. We understand now more than 15,000 people tuned into that. So Victor, the floor is yours to once again wow us with your great leadership.
Yeah. Thank you, Marcia, and thank you for inviting me to moderate this first session. It's a very exciting symposium we put together. I think for this session, we brought together experts with deep experience in grand challenges so that we can inform the NAS in your own deliberation. There are 3 distinguished panelists plus myself will present 4 different examples of grand challenges from the National Academy of Engineering, from National Academy of Medicine, National Science Foundation, and the UN Sustainable Goal Development Goals. So you're going to hear about this. So to provide you an idea what others have done and what you want to do. So I think in many of our questions, and when we rehearse, we ask ourselves, what is a grand challenge? You're going to hear from NSF the idea of big ideas, bold long-term research processes, and ideas that identify future investment at the frontiers of science and engineering. You're going to hear about UN SDG as a blueprint to achieve a better and more sustainable future for all, and they cover the broad range of global challenges. You're going to hear from NAE identifying game-changing ideas for engineering to improve life on the planet. And for the NAM, we define grand challenge as inspire the world to coalesce around shared priorities and audacious goals for addressing big challenges in science and medicine. So in other words, set aspiration goals to inspire collective action at many different levels, academia, government, public and private sectors that can change society and the world. I think we're all in agreement that grand challenge is to make a difference in the world and that we should be bold and think about what's in the future. So I've asked each panelist to present their grand challenge and to address 5 questions. 1, why a grand challenge? What were your motivation developing a grand challenge? 2nd, what is your grand challenge? Describe how it aligns with your motivation, your goals. 3rd, what is your process for developing your grand challenge? 4th, how do you implement it? How do you measure success? And finally, over the course of your grand challenge, did you encounter any unexpected outcome? What are the lessons learned? So with that background, I'd like now to turn over to the panelists. First, I'd like to, let me introduce all of them first. Al Romick, Executive Officer of National Academy of Engineering. Thank you, Al. Don Tilbury, Assistant Director, Directorate for Engineering, National Science Foundation. Thank you, Don. And Elizabeth Cousins, President and CEO of United Nations Foundation and the lead negotiator for US on the SDG. Let me start with Al. Al, can you tell us about the Engineering's Grand Challenge?
Yeah, thank you very much, Victor, and good day to everyone that's listening in virtually. So let's go to the next slide, please. So this started out on a very interesting path. Around the turn of the century, the question was asked, what were the 20 greatest engineering innovations of the 20th century? So a committee was put together. It was funded by the United Engineering Foundation, some internal funds, professional engineering societies. Data was gathered in what today you might call a form of crowdsourcing, a lot of churning, et cetera. And eventually this list of 20 items was generated. And in fact, I would bet that if each one of you took out a tablet, either electronic or old-fashioned paper and pencil, and started writing down what you thought were the 20 greatest innovations of the 20th century in technology, you would end up with a list that looks pretty much like this one. Many of them would be in common. Well, that generated a nice coffee table book, and everyone was happy about it. But then that posed another question. And the NSF came to us and said, can you tell us what will be the greatest innovations of the 21st century? Well, you know, I think most of us believe that if you knew the answer to that, you wouldn't be here. You'd be on your private island somewhere in the Caribbean. That's really not the right question. And so what really that ended up turning into is what are the greatest problems that have to be solved during the 20th century to maintain life on the planet the way that we know it. We formed a standard NASCM kind of committee. It was chaired by Bill Perry. It was financed by the National Science Foundation, and they went through a very deliberative process. They were trying to get to 10 goals, but they only ended up with 14. They ended up with 14 grand challenges that are now going to be shown on the next slide. And so here they are. These are not meant to be in any particular priority order. These date back to about 2008, so they're now a dozen years old. There's debate about whether they should be revisited or not, but in some ways it's really just the idea of what are the important kinds of problems that have to be solved during the course of this century. So here they are. You can see there's 14 of them. You know how they've been generated. And quite frankly, there are a few other things that will occasionally come up that you might actually see sitting at the intersection of these. So people might mention food, for example. Well, that would sit arguably at the intersection of the nitrogen cycle and clean water and perhaps something to do with energy. You can see some of them, Victor, touch on medicines like health informatics and engineering better medicine and reverse engineering the brain. So room there for partnerships. So here's a very nice list. So what do you do about it? Well, the first thing you have to realize is that most of the people that are on this virtual conference today are probably not going to be around long enough in this century to really be able to solve these. It's really about getting the next generation ready to solve these kinds of problems. So next slide, please. That gave rise to something we call the Grand Challenges Scholars Program. It was started by the Dean of Engineering at USC, the Dean of Engineering at Duke, and the President of Olin College. And what they recognize is we're going to need more than just having an outstanding skill in some area of engineering or physical science or whatever else it might be. That companies and institutions are obviously going to look for skills that go beyond that. And out of that fell what we call the 5 competencies of the Grand Challenge Scholar Program. And you can see what they are below. And I can tell you after 36 years in the aerospace and defense industry before I came here, these are in fact exactly the kinds of things that companies look for. A strong basis of talent, being able to work in a multidisciplinary environment. Your ideas have to be ones that make business sense in order for someone to fund them. Recognize that the world and work is done in a multicultural, a global sense, and that whatever you're doing, you need to be socially conscious right up front. You're going to help people and not do some damage to either people or to the planet. Right now, there are over 100 universities in the United States that have put these programs into place. The actual design of the program is very much up to the university. All they have to do is convince us that they will, in fact, cultivate these 5 talents. A couple of very interesting things about this. Some of the metrics we can measure now up front are probably not real meaningful yet. Numbers of students, numbers of schools, for example. But there are some interesting things that we see. For example, women in engineering has been stuck at around 20% now for many years. But yet the number of women that are in these programs is about 55%. So it matches the demographics of the nation. Underrepresented minority enrollment in engineering is much below the population representation, and here it's around 15% or so. So it still doesn't quite mirror the population, but it's several times larger than it is in engineering in general. So it's attracting the right people. The most important metrics are the ones that are going to emerge into the future, and that is what difference will this kind of skills make in people's ability to actually go ahead and solve those problems. So that's probably a multi-year goal, but we'll see how we get to it. But let me end with one final thought, something that's very timely right now. The final slide, please. And this is something new that the National Academy of Engineering has just launched. We call it our call to action for the COVID-19 crisis, and it really merges 3 different generations of engineers. The very basic ideas come out of the students that are in the Grand Challenge Scholars Program. Those ideas then go to a team of alumni from the Frontiers of Engineering, which is very much like our version of your Frontiers of Sciences program. They give it a technical review and vet the ideas. Those ideas that look good go through some I-course kind of training through the Los Angeles node, and then they get passed on to an expert panel of NAE members who try to make the right kind of connections either to companies, funding agencies, venture capitalists, or whatever to pursue some of the ideas to fruition. Just been launched. The last time I checked, there were several hundred ideas that already had been submitted. We've organized the first technical review teams. We've solicited the NAE member volunteers for the final panel, and so it's off to the races, and it's one that will certainly keep you and your standing committee apprised of, Victor, as we go forward. So with that, I'll stop and turn the time over to my colleagues.
Well, thank you, Al. Outstanding presentation. We'll come back to you very shortly. Now, the sequence is Al starts with NAE. I'll talk about NAM because they are both Academy Grand Challenges. We go to Dawn about NSF. And then, of course, we look at this big SDG with Elizabeth. I want to talk a little bit about NAM Grand Challenge. Now, why do we get into it? How do we pick what we pick? And what are we expecting from it? So many of you know that IOM became NAM in 2015. And so the NAM Council and I decided we, as a leading academy of medicine, should have grand challenge to inspire the nation. Later, this turns out to be an important part of our strategic plan, which we made in 2018. But back in 2015, we want to inspire, get people, academia, government, private, and public sectors to act together and to have an impact on health and medicine. So we start learning about what is the Grand Challenge and what did other people do. So we looked at the NAE Grand Challenge, the Gates Foundation Grand Challenge, Clinton Global Initiative, OSTP, Royal Society, and many others, and came with the idea that what we like to do is to be more action-oriented with outcomes so it can make a measurable difference. We formed a Blue Ribbon Committee that developed 5 different ideas. Then we did a membership survey. And then also through the President's Forum, we discussed this and actually landed with initially 1. Because of our bandwidth, we feel we can only do 1 if we want to have action, and we chose healthy longevity. So can I have the next slide, please? I think what you're really seeing in this particular slide is why we chose healthy longevity. First of all, as you all know, this society is aging in a really rapid fashion. That in fact, this 1.6 to 2 billion global population in about 20, 30 years will be over 65. But if you look at the upper graph, it shows you starkly that the aging population is rising quickly. If you look at the gold graph, it shows that it's moving very quickly. And then at the same time, fertility is reducing. The number of people under age 5 is reducing. So what's really amazing is at 2020, we're just crossing through these 2 graphs. So there are more people over 65 than less age of 5. What you see in the bottom is the demographic, what they call population pyramid. In the 1970s, you can see it's a real pyramid. And about recently, it's now becoming very vertical. And I think if we go forward, it can become a rectangle. And in some society, the pyramid has inverted. Now, the implication of aging society, which many of us belong to, if you define 65, lots of chronic disease, strain on healthcare system, financing, disruption in family structure and relationships, tremendous impact on social infrastructure, insurance, retirement, and of course, ultimately, the workforce itself, the size and composition. So we took this on as a grand challenge because I think it affects everyone, as a big part of our society, and we decided to do an international commission to study the practice, the policy, and other areas. But perhaps more importantly, next slide, is the idea of innovation. Because as we look at the unmet need and opportunity, we decided that what we really want is healthy longevity, not lifespan increase, but health span increase. Because by being healthier, we can certainly be more productive, can contribute to society. It's a gain for everybody. Furthermore, with this large population, it is a silver economy. Therefore, if you do well by this, you can do good and do well. But what we found the challenge was insufficient research funding. If you go ask anybody on the university campus, what kind of research do you do? It's cancer, cardiovascular, hardly anybody say aging. And of course, so much research is focused on disease, and we want to look at health span. So the second piece of our grand challenge is to create a global competition. We raised $30 million in an international competition to catalyze transformative ideas, breakthrough, innovation, to improve physical, mental, social health and well-being for people as they age. So you don't have to be 65. But if you look at the health span, this will be phenomenal if you look at how to improve their well-being. The competition is open to innovators from, as I'll show you, many countries from any field, biomedical science, engineering, technology, social science, policy, etc. What we really wanted to do is to create a global movement to attract innovators into the field. Next slide. So this slide shows you how we went about doing this. First, we have a pyramid in which we have the bottom, our Catalyst Award, $50,000 seed awards, which we borrowed from the Gates Foundation Exploration Grand Challenge approach. Innovative ideas, 2-page application, no preliminary data needed. And we were managed to talk to many different countries, and you can see that 50-some countries have joined this. And what's great is that about 8 or 9 funding agencies each fund their own countries as a region, but they work under umbrella to select and to put forward these Catalyst Awards, 450 awards each, all told. If you're successful, you have access to much larger amount of resources, which are funded by J&J Innovation, the European Investment Bank, and the Japan Ministry of Economy and Trade and Innovation, and also with companies coming together. Finally, we raised about $5 million for a grand prize to see a breakthrough. So this, in fact, is our grand challenge. Lessons along the way, organizing international activity. I was quite amazed how excited the Japan NIH, the Singapore Ministry of Health, China's Academy of Medical Sciences and others all joined in. They funded their own, but they work under umbrella as a gold collaborator. So once a year, like NAE, we'll bring together the winners to do a summit. And we hope this will really increase the amount of research and health and longevity. Next slide. The one I just briefly want to talk to you about is a new one that we are beginning to launch and adopt. This is on mental health. This is a big global issue because 450 million people worldwide have mental health illness. 1 in 4 affected by mental health and neurological disorders. Cost the world $3 trillion globally, and about 12 billion workdays are lost. It's the number one cause of global disease burden for disability. And of course, there's hardly any investment globally, which is the big problem. 1% of people's health budget is to mental health. Next slide. So really what happened is the World Bank had a meeting called the Brain Bond. Their thinking in 2018 is that if we raise $10 billion, we can really make things happen everywhere globally. And so with that, I was invited by my good friend Garen Stagland, I'll talk about briefly, the World Bank and others, to see if we can convene the people together. And we did. This is a $10 billion umbrella for financing to actually invest in research, evidence-based intervention, and breakthroughs. And we focus on the younger population, as you can see here, because 70% of mental health are developed during adolescence and early childhood. 3 areas of investment: implementation, how to deliver care better, translation, and of course, breakthrough discovery. Next slide. What's amazing is WHO, World Bank, UNICEF, World Economic Forum have all joined this. And in fact, some of them are making great charges because the World Bank will have to issue the bonds, which I'll talk about later. We have Bank of America, who's actually the lead underwriter, and NIH and others. As you can see, there are many people who have joined us, including Wellcome Trust and others, that actually provide initial funding. Next slide. And of course, we divide this into 4 different work groups and engaging a lot of people, experts. I want to shout out to Garen Stagland, who's the head of One Mind, who's the co-chair with me. We are convening, but this eventually will be a big initiative which will happen outside the academy. That's an interesting model. Finance, use of proceeds. How do you measure success? And what's the governance? And I should point out to you the number of National Academy members who are involved with this, such as Steve Hyman, such as Chris Murray, such as Tim Evans, and of course, Barry Cohn, who leads the Science Philanthropy Alliance, is one of the co-chairs for the finance structure. Last slide. The key thing is to look at how we're going to use this fund. This is going to be a key issue. And what are the things to measure success? But the way the finance works is that we bring together best financing people from World Bank to bankers, you name it, and to create a $10 billion long-term bond, with a mixture of different ways of financing, from direct philanthropy, from municipal and sovereign bonds, to corporations investing, and impact bonds, to different types of investment. And that is done by the whole finance sector. Together with one of the lead is the person who engineered the stem cell initiative proposition, $3 billion in California. So we're getting really good advice from California there. The governance is key. This is not going to be a National Academy's initiative in the long run. We're helping to get started, but we like to create a global nonprofit like the Global Fund, like the Global Alliance and Vaccine Initiative, Malaria Partnership, etc. We're working on this. A 501c3 has been formed and has received initial funding, and this whole thing will be launched in 2021. So I just want to tell you, we see this as action, impact, getting the resources to make it happen. Can't do it alone. So the main thing I learned is how important is the global collaborators and partnerships are. And there are many good people out there who'll be inspired by the ideas that we all develop for better health. Thank you. Let me turn over to Dawn Tilbury and tell you about the NSF Grand Challenge.
Well, thank you very much, Victor. That was a great overview. I'm happy to be here today to talk to you about the National Science Foundation's 10 big ideas. Now, NSF started the process to develop these big ideas in the spring of 2016. Then, it was nearing the end of a presidential administration. It was clear there'd be a new administration in the fall, and the leadership in the foundation wanted to look forward and take the initiative. The goal was to motivate dynamic, fundamental, interdisciplinary research, building on the theme that science is strongest when science works together. Is my slide up?
Yes.
Great. Next slide. Slide 2. So as you may know, NSF is organized into 7 research directorates, from biological sciences through social, behavioral, and economic sciences, and several offices. At a retreat of the senior leadership in mid-April of 2016, each assistant director and office head was instructed to come to the retreat with 2 potentially transformative ideas, but not to talk to each other beforehand. Of course, each of them talked within their directorates or offices, discussing and debating which ideas should be brought to the retreat. After all the ideas were presented at the retreat, synergies became clear as well as overlaps, so the ideas were refined and focused. The key questions that were considered when choosing the final ideas to move forward were, what is the new vision? What are the key research questions that need to be explored in the area? And why is this appropriate for the National Science Foundation? After much discussion, many flip charts, and post-it notes, there was voting on the final ideas. Next slide, please. So here are the ideas that came out of that process. This slide was presented at the May 2016 meeting of the National Science Board. And if you're counting, you might note that there are only 9 ideas here. The NSF Includes effort on broadening participation was already ongoing and was added to the big ideas list later. The Science Board was very excited about these big ideas. They found them to be inspirational and important and could help make the case to external stakeholders such as Congress, the administration, and the general public about the importance of NSF-funded research. The research big ideas, the ones in green at the top, are about fundamental research challenges in areas that are ripe for transformational advances. All of the big ideas are tackling thorny, complicated problems that require contributions from multiple disciplines, which is why they make sense for NSF, because we fund research and education in all areas of science and engineering. Now, in fiscal years 2017 and 2018, the big ideas were launched with invitations to the community to run workshops and conferences and submit small-scale proposals. NSF continued to refine and develop the ideas. Next slide, please. So here are the 10 big ideas with the fiscal year 2019 budgets. The big ideas were formally launched that year with set-aside funding allocated to each idea. We called this the stewardship model, where the funds sat in one directorate, but the funding decisions would be made collaboratively across multiple disciplines. Now, you can note that the $340 million total is out of an NSF budget of $8.1 billion. So this is less than 5% of the overall budget, but we found it has an outsized impact. The big ideas may only start benefiting society in a decade or longer, but they can have impacts on science and engineering knowledge, practice, and workforce in a much shorter time frame. Now, I won't have time to tell you about all of the ideas. You can find much more information on our website, but I'd like to tell you a little bit more about the Convergence Accelerator and NSF 2026. Next slide, please. So the Convergence Accelerator is a new way to fund convergence research, bringing together large teams of researchers with academia, industry, government, and nonprofits. The process is designed to nurture teams and partnerships that speed this convergence research, leading to specific deliverables over the short term. Now, a bunch of teams started working together last summer and will pitch their proposed solutions this summer. After a competition and a down select, a smaller number of teams will get larger amounts of funding to develop their specific deliverables. And you can see the 3 tracks that we're running right now. The second set of tracks will start this summer, has been announced, and there's an invitation to submit ideas for future tracks that are ripe for this type of accelerated convergence research with large-scale teams working together. We're very excited to see how the projects come out. Next slide. Finally, I'd like to mention NSF 2026. This was an effort to get new big ideas and commemorate the semi-quincentennial or 250 years anniversary of the US. We invited the general public to submit their ideas and received more than 800 of them. Went through several rounds of review, and as you can see, there were 33 invited to submit videos. The Blue Ribbon panel chose 7 winners, and cash prizes were given out in February. We're also inviting the broader research community to propose workshops and eager projects in any of the 33 finalist areas. So all of these big ideas, one of which is about getting new big ideas, is about changing the way our communities think and do things. And in order to get the community to change, you need to get lots of people engaged in order to do that. Final slide. In summary, I'd like to acknowledge that much of the material on the origin of the big ideas was presented in a panel discussion at NSF's 70th Anniversary Symposium last February, and you can watch it online if you're curious for more details. Thank you for your attention. I look forward to the discussion.
Thank you, Dawn. Very inspiring. Let me go to Elizabeth. Tell us about the SDG.
Thank you very much, Victor. And it's a delight to be here and really exciting to be part of this symposium. Good afternoon, everyone. Well, I'm going to do something a little bit different and talk about what it would look like if the world decided to create its own grand challenge. In the last generation, we've basically done this at least twice on a grand scale. The first time was the Millennium Development Goals. At the turn of the millennium, world leaders agreed on 8 time-bound goals to improve people's lives around the world in specific and measurable ways. And here were the 8 goals: on poverty and hunger, on education, gender equality, maternal health, child mortality, HIV/AIDS, environment, and partnership. The goals tried to have clear targets. They tried to draw from what we thought we knew then about development, and they got some big results, particularly in health and education. Millions more children completing primary school and improvements even in gender parity. And by some of the most rigorous and conservative of estimates, 20 to 30 million lives were saved because of the MDGs, especially because of investments in vaccinations and reduced mortality from HIV/AIDS, tuberculosis, and malaria and measles. But the MDGs also showed some limitations in how we were going about goal setting. Next slide, please. Some of the goals were squishy, for example, on gender equality, and nobody really felt ultimately accountable for them. Some of the goals measured only some of the right things. For example, getting kids into primary school is part of the battle, but it doesn't say anything about the quality of the education they get when they get there. Some of the goals only tackled symptoms and left fundamentals untouched. For example, taking on a disease, but not addressing the underlying contributors to good health or to good health systems. And the MDGs were also ultimately about foreign assistance. They were about how one part of the world sought to use a limited set of instruments to help another. Worthy and important, but also only a slice of a bigger picture. So in 2015, we tried again. Next slide, please. Now, I was working at the US mission to the UN at the time. And when countries convened on the 20th anniversary of the original Earth Summit, this was in 2012 in Rio, we decided to create a new set of goals that would take sustainability more seriously. We wanted goals that would reconnect our economics to our goals for a healthier natural world and for healthier and more just societies. We wanted to push ourselves to focus on outcomes, not outputs, and the evidence of what drives those outcomes. We wanted goals that were about everyone and not just one part of the world talking to the other. And after 2 years of negotiation, extensive consultations around the world, 193 countries adopted these 17 goals to achieve by 2030, and these are the Sustainable Development Goals. The SDGs are essentially an attempt to reframe entirely what development is all about, to make it about everyone, and especially to connect economic, social, and environmental targets together. And as I say here in this slide, they're not perfect, but they're ours. So where are we today and what have we learned? Next slide, please. Well, first, where are we today? And we can get more into this in conversation if there's time. But at 5 years in, we've seen progress in some areas. More children are living past their 5th birthdays. More kids are going to school and drinking clean water. We're seeing new actors step up for the SDGs, cities who are embracing them as a tool for their own policy priorities, companies who are embedding sustainability into their plans in new ways, youth and civil society activists who are using the SDGs as a relevant frame of reference for their own efforts. And we're seeing a real shift in perspectives about development, in debates about public policy and public investment that the SDGs have clearly helped to stimulate. We are, however, still substantially off track, and that was even before the pandemic we're all living through now. As you all know better than I do, we are nearing catastrophic tipping points on things like biodiversity and climate change. We're facing rising inequalities, including setbacks for girls and women around the world that just shouldn't be true in the year 2020. And obviously, the COVID pandemic exposes and exacerbates all kinds of inequalities and structural challenges and vulnerabilities that are at the heart of what the SDGs were trying to remedy in the first place. So we are behind, though in my view, that makes the goals more important than ever. So a few things we also learned about goal setting. Now, I've indicated a few of them here on this slide, things that we learned in the lead up to the SDGs and from the first several years of trying them. One is the importance of a common language about what we're trying to achieve, the importance of a common framework and shared metrics for evaluating progress, the importance of tackling the intersections across issues, the interdisciplinary questions that were raised already, and of getting out of our silos. And just here, a really quick sidebar. We struggled so much in negotiations over this because some of the most critical intersections, whether it's the nexus between food, energy, and water, or governance questions, or any number of other ones, don't always have ready-made fields of inquiry or practice, and they often don't have good metrics. So we were often struggling with a choice about whether to leave the hard-to-measure but critical issues off the table, or whether to include them, and then figure that part of our effort had to be working to build the knowledge and build the evidence and build better metrics and science around them. We obviously chose to include those. But the biggest thing we learned may be that as an extremely diverse world, we actually are capable of setting collective goals, and we're capable of setting them around issues that really matter across politics, geography, or disciplinary difference. So just a final word to conclude around the COVID context. So much of what we need to do to recover, to rebuild, to do the building back better that people are now talking about goes to the heart of what the SDGs are about in the first place, because they are ultimately designed to be a grand challenge that aims to inspire and energize people around a blueprint for a more just, sustainable, and peaceful society. And I can't think of anything more exciting than the ability to use some of the techniques of grand challenges and the kind of just extraordinary brainpower that is online in this symposium to mobilize the scientific and research community around the sort of science and solutions we need to reach even some of those outcomes, because they really do matter and they matter to everyone. So thank you very much, and look very forward to the conversation.
Thank you very much indeed. We have about 10 minutes for a Q&A, and I have 3 categories. One is, how do you actually get many of you have addressed about the process, how you got there, but how do you get the buy-in, if you will, of your constituents, if not the world, from academy and NAE to the NSF? I can imagine the science community can say, you're now being directing what we should be doing. And SDG country will say, yeah, what are the resources? And for me, my members will say, what are you trying to do? Do this. How about in US? So let's talk a little bit about your effort to buy in. Second is the measures of success. And third is the impact that you believe that you've done. And then I have a final question for all of you. So quickly, can I start off with Al, the communication buy-in for your members and the engineering world?
Yes, I think, certainly for buy-in of members, that happens by having the leadership of the Academy go out and talk with our members, write about it, etc. But one thing that's very novel, we began a program jointly with the Royal Academy of Engineering in the UK and the Chinese Academy of Engineering homed in Beijing, and started a series of Global Grand Challenge Summits, of which we did the first one in 2013, that was in London, and then 2015 was in Beijing, 2017 was here in the US, 2019 was back in London, 21 depending on the virus, could be back in Beijing and then here again. And the interesting thing about those is all three of the societies have embraced it. The British, for example, are looking at how it interfaces with the strategic development, sustainable development goals of the UN. But I think the most fascinating thing to us is of the 900 or 1,000 attendees, half of them are students that come from around the world, which really has industry excited and made them willing to support these events in exchange for having the ability to interact with and potentially recruit students. So that, I think, is our flagship for international.
I'm going to have to move quickly. Dawn?
Yeah, so at NSF, as you completely are correct, the community is like, you're taking our money away from our core programs and putting it to these other things. But I think we've been pretty effective in communicating to the community that the big ideas are where they can all participate. There's a role for pretty much anybody in science and engineering in one of the big ideas, and they should see this as an opportunity to increase the impact of their research. Not everybody has to do it, but I think it's a great opportunity.
Right. Elizabeth, 139 countries. Boy, that's like
193.
193, excuse me.
60.
Yeah.
Yeah. Well,
so how do you get the buy-in? I mean, I can imagine the poor country says, I have no resources to make it happen, so I'm going to look embarrassed when I don't make it happen.
Yeah, I think, several things. This was 5 years ago. We had a level of political leadership from a number of capitals that was crucial. The negotiations were structured very differently, though, than normally, and I could get into the details if we had more time, but it basically meant that there was more of an even playing field at the negotiating table, and we took 2 years to negotiate them. So we had every country represented, and represented in a way that they felt they were peers, and we listened to one another, and we took a lot of time on the front end to learn together. We actually took several months at the beginning just to get briefed up by people like you, to understand things we didn't begin to know, to establish that common vocabulary so that we did create a level playing field. And I think there was just an awful lot of mutual respect and give and take. So part of it was just that simple factor of listening to each other, taking each other seriously, and incorporating that into the final outcome.
I can tell you in the health world, SDG 3, making a huge difference. Even though we're not going to meet universal health coverage by 2030, there's a tremendous effort out there. So you are making impact, and your measurements are clear. How about you, Dawn? Are your measurements of success very clear? Are you making an impact?
So, some of the big ideas are different to try to measure the impact. I think we're still trying to figure out. We formally launched these in fiscal 2019, so we're only partway through the second year of full funding. I think we are looking at different ways to measure the impact, but I don't think we have the answer yet.
Al, you just told us how you did it. Are you feeling good about this?
Yes, we are. Obviously, we, as I said, we're planning now to have the second event in Beijing, followed by one in the U.S. The number of schools continue to grow. In fact, it's gotten to the point where the growth of the Grand Challenge Scholar schools has actually become organic, and we didn't need to do very little in order to have the movement spread.
So for us in the health and longevity, the impact is huge because let's look at how many applications we receive. In Grand Challenge for Gates Foundation, 300 per call, we have received over 1,000. And globally, a lot more. And I think we're mobilizing to say this is an important area. We think that eventually we'll be able to scale it up, not only to help everybody to get healthier, but the whole economy can benefit from it. My question for every one of you, my last question is, did your Grand Challenge prepare you to respond and prepare to the current COVID-19 pandemic? Are your Grand Challenge positioned in such a way that even though they're not directly in a topical way, but in fact, they're preparing the organization and the world better for a challenge like COVID-19 pandemic? Can I start off with Dawn?
Sure. I'll say that one of the 10 big ideas is the future of work at the human technology frontier and how people interact with technology to get their jobs done. And I think that's absolutely what we've all been doing over the last many weeks. And how we can better understand that and leverage that, I think, is the kind of thing that NSF research is leading towards.
Right. And Elizabeth?
Yeah, two elements. I would say first, the degree to which the SDGs emphasized health systems and also the interlinkage across other systems, economics and others, is actually really fundamental for understanding and responding in a crisis like this. But I think the second thing I would mention is just the SDGs showed us that people are capable and countries are capable of cooperating around something that they care about in common. We are obviously on a bit of a back foot these days when it comes to global cooperation. So I look back to that barely 5 years ago, the SDGs, when countries showed themselves able to compromise, to negotiate, and reach agreement on such foundational questions for all of their own societies. That gives me a tremendous amount of hope and strength and a sense of what the solution needs to be going forward, both to COVID and to other collective challenges that we face.
Al?
And I think for the NAE, our cross-generational call to action does exactly as you ask, Victor, getting a new generation engaged. And in fact, more so than perhaps solving the COVID-19 issue of today, is preparing an entire generation to solve those kinds of issues as they arise again in the future and over the rest of the course of this century.
Yeah, and for us, I would say the two topics, aging, and that's the vulnerable population during COVID. So we already organize and get people together to say, what can we do in this area? And mental health, another big issue. We expect a surge in mental health, someone called that the second wave, if you will, and actually getting the organizations together to say, how can we make a difference is huge. Let me thank all of you. I think what I've learned is inspiration, goals and setting, share goals, and being able to get buy-in and being able to make an impact. So it's been phenomenal. I hope this is helpful to you, Marcia, for the rest of your conversation. I kept my word. I'm right on target. Thank you.
Well, welcome to panel number 2 of our plenary session on grand challenges. Now, in this panel, we're going to hear the views of candidate challenges from each of the classes. Each of these speakers has been put forward by the classes of the National Academy of Sciences based on their ability to be visionary. Now, please don't think that they are in any way under orders to be representative of the sections within their classes. Rather, they were charged with coming up with inspirational ideas of grand challenges that could get everyone's thought juices flowing. Now, let me briefly introduce all of the speakers so that they can go in order of their classes briskly, and I won't have to introduce between them. So representing Class 1 is Maria Zuber. She is the E.A. Griswold Professor and Vice President for Research at Massachusetts Institute of Technology. She's a geophysicist. Representing Class 2, which is biology, is George Church. Professor Church is the Robert Winthrop Professor of Genetics at Harvard University. Representing Class 3 is Cherry Murray. She is a professor of physics and director of Biosphere 2 Institute at the University of Arizona. Representing Class 4 is Stuart Orkin. He's the David G. Nathan Distinguished Professor of Pediatrics at Boston Children's Hospital. Representing Class 5 is Charles F. Mansky. He's the Board of Trustees Professor in Economics at Northwestern University and also the Board of Trustees Professor of Economics. And representing Class 6 is Pam A. Matson. She's the Richard and Rhoda Goldman Professor in Environmental Studies and a member of the School of Earth, Energy, and Environment at Stanford University. So, Maria, the floor is yours.
Great, thank you. Can you bring up the first chart? Thanks. So, good afternoon, NAS colleagues and members of the public. So, I am honored to represent Class 1 to talk about arguably the grandest of challenges, the question of whether there is life beyond Earth. It's a long-standing question, and why is it so difficult to answer? Well, it's actually quite obvious why it's so difficult. First of all, the universe is a big place. A typical galaxy, like our Milky Way, has 100 billion stars, and there are about 3 trillion galaxies in the observable universe, which means about 7 trillion known stars. So you have to believe that the odds seem pretty good, but the scale of the search is daunting. Second, we really don't know what we're looking for. We know how to identify Earth life, and so that's a good place to start. Life as we know it requires three primary ingredients: liquid water, a source of energy for metabolism, and the right chemical ingredients, primarily carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, etc. Because liquid water is common to all life on Earth, we sometimes frame the search for life beyond Earth as following the water. So if we could go to the next chart, please. So let's start by looking at promising possibilities in our own solar system, places that are far away but accessible by spacecraft. So first of all, on the left, we have Mars. There is incontrovertible evidence that Mars has abundant water ice at very shallow depths, within a meter of the surface, and we don't know how deep it goes. Some of this water ice melts and seeps to the surface during Martian summer. But water isn't stable at the surface because the atmosphere is so thin. If life ever existed on Mars, it may have retreated below the surface, so developing a subsurface sampling capability is critical, and the deeper the better. Recent observations from the InSight lander show the Martian crust to be highly altered or fractured to a depth of about 10 kilometers. In the middle there, we see Europa. Europa is a moon of Jupiter, and it's known to have a subsurface ocean that scientists and engineers are working hard to design a means to access it. The ability to probe deeply beneath the surface is critical because in most places, it's likely 15 to 25 kilometers beneath the surface. And we're hoping to get lucky and be able to find pathways to the surface that are much shallower than that, but it's not guaranteed. And then over on the right-hand side of the chart is Enceladus, which is a tidally heated moon of Saturn that emits geyser-like jets of liquid water and ice particles that could be sampled by a spacecraft flying by. Now, exploring the outer solar system is technically extremely challenging, but it's feasible based on successes from missions such as the Cassini mission. Now, in all three of these cases, we're searching for microbial life. And what could that conceivably be like at any of these destinations? If life evolved independently from life on Earth, it probably uses an informational polymer. It's likely based on nucleic acids, and it may use alternative bases, or then again, maybe not. We just don't know. Okay, can I have the third chart, please? So let's now leave the comfortable confines of our own solar system and think about life, the possibility of life in other planetary systems. Over the course of less than a generation, the potential of life existing beyond our own solar system has improved dramatically with the discovery of planets around other stars. The first exoplanet orbiting a star similar to our sun was discovered only in 1995, and the current census contains over 4,000 exoplanets. Nearly all Earth-like stars that have been sampled have a planetary system, but we need to determine if any of these could harbor life. While our dream is to detect life directly, the focus now is on determining habitability, such as the presence of liquid water or the existence of a magnetic field that could shield energetic cosmic rays. Planet-finding missions, such as Kepler or the currently operating mission TESS, are identifying promising worlds, but space experiments to detect signatures of oxygen, water vapor, and methane are complex, expensive, and years in the future. Great projects for scientists who are just starting their careers. Even the most complex and ambitious missions that are being planned would resolve Earth-like planets around other stars to just a handful of pixels, as you see in the simulation on the left there. And our challenge is to figure out just how much information we could glean from a handful of pixels that could point to the existence of life. So let me close here by noting that the answer to the question of whether life exists beyond Earth is profound, no matter what the outcome. Either the inhabitants of Earth are special or we're not, and both answers are interesting. So, Marcia, thank you very much, and I'll turn it back over.
Fabulous, Maria. Much food for thought. George Church, you're up next.
The grand challenge I'm addressing is how can we use synthetic biology? So happy day after DNA Day. Let's talk about maps. Clear roadmaps can stimulate innovation without restricting it. Specific examples can inspire all generations, from the freshest to the wise, to imagine and implement solutions for poverty, inherited and environmental risks, sustenance, and manufacturing. First and foremost is ethics and equity. One overarching grand challenge for biology and medicine is to equitably benefit all people on Earth. Poverty, whatever the causes, can be reduced by a virtuous cycle. Any alleviation of diseases, infectious, genetic, nutritional, or neuropsychiatric, can lead to improvement in education, then finances, then health advances, and so on to the next cycle. This is suddenly plausible due to exponential improvements in cost and quality of biotechnology. It's been a 10 million-fold recent, so far, change in reading and writing DNA, and hence our ability to test all sorts of ideas, basic and applied, about biological systems, materials, organs, ecosystems, with positive societal impacts. We can even reduce the cost to zero for every person on Earth. For example, extinction of major human pathogens and improved agricultural germlines. We can use genome recoding to make any organism and human cells resistant to all viruses in nature, even viruses we've never seen before. Second is inherited risks. We know how to enable all people to be free of serious inherited diseases, to cure and prevent these via nearly free whole genome sequencing and genetic counseling well in advance of conception. This could save trillions of dollars in untold human hardships. Therapies are a little harder, but costs drop for large markets, and the largest market of all is 8 billion people afflicted with the most common disease, which is aging. This has suddenly leapt from pipe dream to hard science. For example, genetic and epigenetic modifications have been shown to greatly extend longevity in animals and to reverse aging in human cells from 100 years old to embryonic and anything in between. These breakthroughs are leading to an abundance of tests, gene and cell therapies, and transplants manufactured from human stem cells or humanized animals, unlimited by scarcity or quality of organs from living humans. Third, environmental risks. To prevent the next pandemic, we may come to expect local and global bioweather maps with high resolution in space and time, surveillance of allergens, pathogens, and drug resistance impacting humans, animals, and plants, natural or engineered, via data pooled from wearable monitors, smartphones, and so on. To dodge these pandemics and other global catastrophic risks, we need colonies in space. But first, test these at scale on Earth with immediate value added, fully sealed recycling, safety from radioactive fallout, pathogens, pollution, zero commuting, possibly more affordable and sustainable than current housing via things like compact photosynthesis of foods and materials. Finally, fourth, manufacturing. So speaking of materials, we can make a wide variety of objects at atomic precision, not in multi-billion-dollar clean room silicon fab labs, but via biology with trillions of 3D bioprint heads per cubic millimeter, with rapidly expanding flexibility via novel amino acids, chiral chemistries, bacterial nanomagnets, sponge optical fibers, and doubling times of 15 minutes. Biosystems can store data and compute 1 million times better than inorganic systems, at least for some, but not all tasks. And the rate of improvement for biotechnology is generally faster. Biology already assembles, self-assembles, and self-repairs 500 gigatons of smart materials every year for free. Now, this is just a modest sampling of the ongoing revolution in basic sciences toward increasingly swifter, safer, and more impactful applications. A remarkable fraction could engage and benefit from participation from non-scientists, just as weather, astronomy, culinary, and gardening sciences have in the past. So please spread the word. Thank you.
Thank you very much, George. Leave it to you to give us so many grand challenges that it will be hard for us to ever determine how we could manage to address them all, but it's better to have an abundance of riches than not enough. Okay, next, Cherry Murray, the floor is yours.
Hi, I'm Cherry Murray, and Marcia, I'm chair of Class 3, and I did consult with Class 3. And Class 3, which is Engineering and Applied Sciences, believes that among the grand challenges of NAS, whatever it is, should be the United Nations Sustainable Development Goals. You heard a great introduction in panel 1 by Elizabeth. For short, these are called the SDGs. They were adopted by 193 nations in 2015. After 5 years, they are more relevant than ever. This is basically about sustaining life on Earth. Even now, we realize that only 4 months into this pandemic, there's a major backward trend in achieving these goals, as Elizabeth pointed out. And this requires the attention of the scientific community, exemplified by the academies of the world. This is a global effort. Indeed, the Inter-Academy partnership of over 145 academies of science, engineering, and medicine in over 100 countries, for which I am one of the 6 co-chairs, embraces the SDGs as an overarching mission. For a succinct description of the SDGs, I will just quote a wonderful quote from the 2015 resolution of the General Assembly. We resolve between now and 2030 to end poverty and hunger everywhere, to combat inequalities within and among countries, to build peaceful, just, and inclusive societies, to protect human rights and promote gender equality and the empowerment of women and girls, and to ensure the lasting protection of the planet and its natural resources. We resolve also to create conditions for sustainable, inclusive, and sustained economic growth, shared prosperity, and decent work for all, taking into account different levels of national development and capacities. So every nation on Earth. The agenda is deliberately ambitious with a set of 17 integrated goals to guide all nations. What do these have to do with science? Attaining these goals must bring together the scientific understanding of the atmosphere, the hydrosphere, the geosphere, the biosphere, and the anthrosphere, human activities, as a complex, interactive, and hopefully symbiotic system. It's transdisciplinary. It includes all the disciplines of all NAS sections and beyond. And its challenge is consistent with Goal 1 of the NAS strategic plan: address critical societal and global issues, catalyze actions, build communities across disciplinary and cultural boundaries, increase capacity in the US and abroad. In 5 years, we've made substantial progress in many of these goals. For the sake of time, I will provide one example. Goal number 2, in gold on the slide, end hunger, achieve food security and improve nutrition and promote sustainable agriculture. The prevalence of stunting, being too small for one's age due to chronic undernourishment in children under age 5, has decreased from a staggering 36% of these children worldwide in 1990 to 22% in 2018. That's a remarkable accomplishment, but it's still 150 million children. Also, there were 800 million people who routinely confront hunger in 2019. Other goals, as Elizabeth mentioned, such as climate action and I will say sustainable cities, have had far less progress. What stands in the way to implementing these goals? Mostly social issues. This is great for social science. Vested interests and political will. A global trend towards populism and nationalism, fake news, pseudoscience, even anti-science. And the impact of COVID-19 is rather massive. For example, the Global Report on Food Crisis 2020 estimates that of the 800 million with food insecurity, before the pandemic, there were roughly 135 million people in severe food insecurity, crisis or worse. That estimate has now doubled due to COVID-19. And every one of the SDGs is profoundly affected by this crisis. An unforeseen positive, we're doing an unplanned experiment in quick removal of anthropogenic forcing, where satellite photos and air pollution indices have shown a major reduction of air pollution in Beijing, Delhi, and other parts of the world during economy lockdowns. Despite these daunting setbacks, how do we get back on track with the SDGs? And what would be the outcome of achieving these goals? One of the repercussions of this pandemic is a demonstration of how fragile our ecosystem and biosystems are. It is no longer possible to retreat into nationalism. We have become too many, and the earth too small through technology. We depend on each other and our environment for our economies, our livelihoods, and our well-being. Resetting our goals again to the SDGs will be the best way to rebuild our economies after COVID-19. This is a huge undertaking. Much of what life as usual will be changed moving forward. For NAS, this grand challenge would be a call to action for scientists involving rethinking how our cities and healthcare systems are designed, transitioning our economy to circular, and our energy sources to renewables, and definitely becoming more prepared for managing disasters, such as future pandemics and climate change. If this happens, then we will have achieved SDG 17, a partnership for the goals, and a sustainable human civilization in harmony with each other and our planet. So I thank you.
Wonderful, Cherry. Thank you so much for that explanation of why the SDGs are still so important and worthy of the National Academy's attention. Next up is Stuart Organ. Please, the floor is yours.
Yes, hi. Thank you for asking my participation. In my comments, I believe there are clear links to some of the prior remarks, specifically those of Victor Zhao and George Church. The comments are mine, but with input from some members of Class 4. As we're confronting the current pandemic, the need for rapid development of new and effective therapies cannot be more evident. While we have witnessed an enormous explosion of biological sciences and related disciplines, the route to identification and development of new therapeutics has not kept pace. Here I propose a challenge that we seek to leverage science for faster, safer, more effective, and cheaper therapies. Next slide. Over the past 2 decades or more, data sets relevant to biology and disease have grown at an unprecedented pace, and new tools have been developed in numerous areas, including but not limited to some here: biochemistry, cellular biology, immunology, etc., down to imaging, computation, modeling, systems biology, nanotechnology. In parallel, as the tools enabling large-scale studies have improved, humans have become the central focus for biological studies, leading to increasing sets of phenotypic data in normal, stressed, and disease states, elucidation of genetic variation on a population scale, emphasis on precision medicine, tailoring specific therapies for genotypes or disease subsets. We have new modalities, including gene therapy, gene editing, and other treatments. With the expanding toolbox of these modalities in human data, we're faced with a major challenge. In short, how do we make the most of these assets while confronted with limited resources, both in terms of finances and people? Next slide. The challenge then is to more successfully harness existing and emerging data and tools to accelerate safe and effective therapies to prevent or reverse consequences of disease, whether inherited or acquired, environmental stresses, climate change, infectious disease, etc. The current path we take for disease therapies is really shown at the bottom, where we take a perturbed state, we do in vitro discovery, in vivo testing, move things to therapy. This has an extraordinarily high failure rate, so-called translational valley of death. It takes a long time to succeed, often years, and it's expensive, many millions of dollars to develop a single therapy. Next slide. In contrast, I think we should envision a new path that leverages the scientific assets we have to accelerate therapies, resulting ultimately in higher rates of success in the majority, not the minority, of instances of identification of targets and for specific entities, a shorter time to success, months rather than years to develop therapies, and cheaper therapies ultimately, which will lead to globally more accessible therapies in the end. This will involve innovation at each phase, not only the science, but also include ways to accelerate definitive clinical trials to shorten time to delivery to patients. Thank you.
Wonderful, Stuart. Thank you. That's nothing less than an entirely revamp of our discovery to product system. So quite a challenge. Yeah. So next up, Charles Minsky. Charles, the floor is yours.
Thank you, Masha. I'm an economist, and economists have a reputation for being dry and practical. And you can see that already on my slides, which are dry PDF text slides. And the challenge that I'm going to discuss is extremely practical. I wish I could talk about something visionary, but I feel like we really need to talk about something very immediate rather than visionary. And that's a call for integrated study of social, biological, and physical systems. And I want to give a little bit of background and then give two prime examples that I think will be obvious to most everybody. First is background. Humans obviously are quite complex organisms, each of us as individuals. The social systems within which we interact are an order of magnitude more complex than each of us are as persons. And to get yet more complexity, our social systems are embedded within a planetary biological and physical system. Now, to make progress when we do our research, it's very hard to study everything at once. So there's been a long standing practice in the social and behavioral sciences that when we study individuals in society, we commonly assume that the biological and physical environment is predetermined. So it's out there. We know what planet we're on and what its features are, and then we study how we behave inside that system. And that simplifying assumption is often reasonable. Often it's the only way to make progress. However, it's not tenable to maintain that assumption when humans significantly modify the biological and physical environment. And humanity has now become so widespread and large that we do significantly modify the biological and physical environment. So the challenge then is to develop the science to enable credible integrated study, and the term integrated is the key word, integrated study of social, biological, and physical systems. Now I'm going to give two prime examples, and I would expect that for NAS members, they would be obvious at the outset. The one that has some history is study of climate change. So if you think historically, climate research was initially a subject for study by earth scientists who seek to forecast the impact of emissions on the planet. Now, earth scientists generally have a physical science background, so it's natural in the early literature on climate research to focus on the physics of climate change rather than the social causes and effects of climate change. However, people recognized long ago that since climate change, in the modern times is initiated by human action, that you can't just look at the physical side. So there has been a development of what are called integrated assessment models over the past 30 years. And so social scientists now do work with physical scientists to integrate the study of the social systems with the atmospheric, oceanic systems, and so on. So where is this and where's the challenge? I think what we've accomplished thus far is that we've achieved a somewhat sophisticated qualitative perspective on how our planet and our social systems interact with one another. So we can easily think this through in a qualitative way in flowcharts and so on to see the feedbacks and so on. But what we really are very much lacking is in our ability to make credible quantitative forecasts of what will happen in society and on the planet as a whole. Integrated assessment models do produce forecasts 10, 20, 100 years out, but it's a very difficult, it's complex empirical research, mathematical modeling problem to do this. And I think it's fair to say there's a very, very large amount of uncertainty in the numerical forecasts that are made. Okay, so that's where I'll talk about climate. And the second one that I want to talk about is quite obvious. It's been on my mind for a long time, but of course the last few months have made it quite obvious to everybody, is the study of pandemics. So if we think about integrated study in pandemics, then we would have to consider altogether population health, the economy, and social welfare. And here there's quite a parallel in the history between the study of climate change and the study of pandemics, is that whereas study of climate change originally came from the physical sciences and focused on that, the study of epidemics and pandemics obviously came from the biological sciences, particularly from epidemiology. And here the history is that epidemiological modeling has been performed by quantitative researchers with expertise in medicine, biostatistics, and public health. The problem with the study of pandemics is that we are really at the absolute beginning of integrating epidemiological modeling with social science research. In the climate area, we've had, let's say, roughly 30 years where economists and other social scientists have been talking with earth scientists, and so some progress has been made. But it's extremely unfortunate, and it's become quite obvious in the past couple of months that there has been no similar exchange of ideas between epidemiologists and social and behavioral scientists. The epidemiologists find it natural to focus on health, considering other impacts of pandemics to be beyond their purview. This is very explicit in the work done, and I think most everyone's aware of this now, the work done at Imperial College in London, which has influenced policy in the UK and the United States, and also the IHME work in the United States, which looks at health systems alone. And we just don't have the integration with the social sciences. And I have to say, particularly with macroeconomics, which is the key thing that's missing right now. So I want to conclude by saying, I wish I could be visionary and talk about what we should be doing over the next 100 years. But we have a quite pressing, I would say, an emergency need right now for epidemiologists to work with social scientists to develop data and models for credible integrated study of pandemics. Thanks, Masha.
Thank you very much, Charles. That was terrific. All right, and now to our final speaker in this panel, and that is Pam Matson. Please, Pam.
Great. Thank you, Marcia. I'm very pleased to be part of this this conversation today. And I'm representing the Class 6, which is Applied Biological, Agricultural, and Environmental Sciences. It's a class that includes social science, biological, and physical sciences all together. Many of us in this class carry out research that contributes both to fundamental understanding and at the same time to problem solving and development of solutions. And so I'd argue that much of what we do falls in Pasteur's quadrant. Given that, it's not really surprising. Could I have the next slide, please? It's not really surprising when I asked members of our 4 sections to share their ideas about grand challenges. A majority of the ideas that came through were really addressing societal challenges. They were articulated in beautiful, elegant ways, in scientific terms, but they dealt with climate change, reducing and adapting to climate change, unlocking the potential of biological resources to feed humanity, understanding mechanisms of susceptibility with COVID on top of everybody's mind, agricultural pandemics, et cetera, et cetera. And, it was clear that basically our members are fundamentally motivated by the goal of human well-being with equity and justice, not just today, but over the long term, as well as the well-being of the planet's life support systems and the species with whom we share the planet. So if we think about addressing this list of societal grand challenges, could I have the next slide? We're obviously going to need to bring lots of resources and assets to bear on this. And we need the contributions of all of these asset groups that I've listed here. And I think we just heard from Charles of really good examples. For example, if we're going to address climate change, we need new technologies that reduce greenhouse gas emissions without having unintended consequences on health or environment. We need to protect and manage land and water resources in different ways than we have been. We need the institutional frameworks, the economic policies, the partnerships and governance systems that will allow this to work. And I think you can go through COVID and see exactly the same thing. And I think the really crucial thing is that if we are successful in building one of these assets, one of these resource bases, but not the others, we won't succeed. So we need a system of resources in order to succeed. And of course, we need the science. Could I have the next slide? We need the science-based understanding to make sure that all those assets are actually in place. And we already have a huge amount of information, fundamental knowledge about each of those big groups. And I suspect we could all list a series of really important scientific questions that need to be addressed. And this engages everybody in our national academies, the world's national academies, and beyond. But what's really important for us to do as we do this is to identify the knowledge that is needed for a system level change so that we have all the pieces. We have a supply chain of the knowledge that we need in order to actually address the grand societal challenge. And beyond that, next slide, please. Maybe most important to me, given that I have a very high level of pragmatism, it's the research challenge of learning how to move from the science to practice at scales that actually matter. That's the hardest question in my own research. It's the hardest thing I run into in trying to teach how to pursue sustainability. We need to learn. And this is partly through, I think, really deep scientific engagement and analysis of ongoing efforts towards societal change. We need to learn how to deal with complex social environmental systems. Complex systems are well studied in theory, but what happens in reality? We need to learn how to adapt because we're living in an uncertain world. We need to be able to promote equity and justice. We need to be able to foster innovation, to learn how to collaborate and partner successfully, to develop and test and use measures and metrics that tell us how well we're doing in our efforts, and figure out how to scale things so that we have transformational change, not just incremental change. So lots of really critical questions there, I think, and they add up to a different kind of grand challenge. Could I have the next slide? One that, in fact, was a take-home message of a recent annual review by Bill Clark and Alicia Harley at Harvard, and where they identified the need to build operational capacity to support action for sustainable development in their case, action for any societal challenge. And so I think we really need some bold scientific initiatives that include within them the job of moving knowledge into practice as an integral part of the research process. This is research to discover what works and what doesn't, to figure out how to understand and train people on how to do that job better, reward people who do it, and so forth. I think bottom line is there's a gap between what we know and what we in society do. And science has a responsibility to help close that gap. I'd argue that without addressing that challenge, progress toward any one of the challenges or societal challenges that we select will be slow. Thanks. Back to you.
Wonderful. Thank you so much, Pam. It's amazing how many of you picked up on this theme of moving knowledge into practice. That was something that was in so many of these presentations. So let me begin by a question for each of you that you might say a few words about that presages a bit of panels 3's discussion, and that is the topic of convergence. You all are roughly familiar with the idea of convergence, which is more than just interdisciplinary research, but really the radical integration of different fields all on the same level, where students are conversant in the vocabularies, in the ways of addressing problems and problem solutions from wildly different disciplines such as engineering, mathematics, data sciences, biology, geosciences, etc., such that they can actually solve problems that have been intractable. And, you know, I heard in many of these presentations inklings of the need to reach across different boundaries, certainly in Charles's presentation, in yours, Pam. Could each of you maybe mention whether you believe that addressing these grand challenges would require or would benefit from different ways of educating? So anyone want to take that on?
So this is Cherry. I will take that on. I absolutely agree that it is incredibly important to educate for any of the grand challenges that you just heard about, which are pretty remarkable challenges. The integration of social science, ethics, which is verging on humanities, physical science, bioscience, geoscience, and engineering. And it would be wonderful to have team work addressing societal problems, as Pam was talking about, in our curriculum of those people who are coming from those disciplines.
Yeah, I'll add if I can. I absolutely agree. I think what we need are educated, well-trained scientists and engineers who understand the broad challenge, understand the language of the broader challenge, and are bringing something themselves to it. And so I absolutely believe that disciplinary expertise is still necessary in all of this, but being able to have that ongoing conversation, not just with other scientists, but with decision makers who are out in the world trying to struggle with these things, is important. And then the interdisciplinary education, I think we've seen huge success in training students who have depth in more than one area and are able to ask questions that many of the rest of us can't ask. And they're essential for this package too.
This is Chuck. I'd like to add something about attention that I think we all recognize. In economics, one of the earliest things students are taught is about the value of division of labor and and specialization. And we wouldn't have a modern society without that. And that does lead people, to go off in their own directions. But there is this, but now, of course, we have all this recognition of the importance of interdisciplinary, transdisciplinary research. But there is a tension between the two, between depth and breadth. And in terms of educating the next generation, we can't have everybody be generalists, because then it's all going to be superficial. They've got to dig in somewhere, but yet they have to recognize the commonalities that are required to work with other people. So, as I say, a couple of things about that. One thing that at least from my perspective, is extremely important is to have a common language. And for the kinds of work that I always see, that common language is mathematical language. And when I was talking before about epidemiologists and economists, I think epidemiologists and economists should be able to talk with one another. And certainly, of course, climate scientists who are mathematically oriented should be able to talk with quantitative social scientists, and we can understand each other in that respect. The other thing to say is that even if you have common mathematical language or whatever language it is, there do get to be big cultural differences across disciplines, and they can be very hard to overcome. And those of us who spend a lot of our time working on NASM and National Research Council committees, where we constantly are coming into contact with people from different disciplines, we know that it takes quite a while. It takes several meetings to just be able to learn the commonalities of language and then to do something useful. So my sense is that we all know we have to move in this direction to bring things together, to the convergence that Marcia was talking about, but I don't think we've quite yet figured out exactly how to do it.
Yeah. So
I would say, Marcia, if I could just add very quickly, is that all of the problems that my colleagues here have talked about here today, they all represent complex systems, and you really can't address problems of that complexity by just being deep in one area. So, so the combination of the depth needed in a particular discipline and understanding, some level of understanding of breadth to be able to deal with complexity, I think is crucial.
Right. Well, your comments all remind me that anytime I was able to step outside of my own narrow lane and work with other groups on a broader problem, I hearkened back to an introductory course I took somewhere that gave me the vocabulary to be able to speak to others. And I remember hearing that you learn more new vocabulary in an introductory biology class than in Spanish 1. And without that vocabulary, you can't even start. And you also learn how they approach problem solving. And if you don't understand how they approach problem solving, then you don't have a basis for interacting either. So I think those are important things to remember. I have one final question before we get on to panel 3, and that is, we heard in these grand challenges everything from the most basic of scientific questions. Are we alone in the universe? Or how did life begin? Where did we come from? To some of the very most practical, how do we sustain life on this planet? What are your thoughts on the balance between the two? Because, when I opened this session, I talked about going to the moon. I mean, certainly no one thought at the time that there was an immediate practical benefit from going to the moon, and yet it inspired a generation. What is the balance between grand challenges with a very practical outcome versus those that simply allow us to dream?
Yeah, so Marsha, I'll start because I'm the one I think who's way out there, and at the current time when we have a crisis, those of us who can, as many if not all NAS members do, who can drop everything and work on the current situation, that's the appropriate thing to do. But we can't stop dreaming, and the day we stop dreaming is the beginning of our demise as a species. And in the course of our dreaming, we will discover things that will help us solve many of these practical problems.
I'll add, I agree with that. It's interesting because when I think about the kinds of research that I see and that I actually heard from members of Class 6 and that I do myself, there's a lot of discovery in there. There's total excitement about the discoveries that we're making, but that also have some important relevance to problem solving. So we don't have to completely separate these things. Even if we set grand challenges, let's think about how to set them so that we have the opportunity and the excitement of discovering how the world works at the same time that at least part of that becomes very important in dealing with these huge challenges. We are not in a situation right now on the planet where we can just set aside these most challenging societal issues. Because we won't survive that way. But I think we can do both.
Well, I thought George Church's challenges that he put forward were a beautiful example of having such fundamental basic science behind them, but it didn't take any imagination to see how they addressed fundamental societal questions as well. And I'm sure all of yours have, as you say, Pam, fundamental science behind them, but basic applications too. And in fact, there was a lot of good basic science that came out of going to the moon as well in the end. So anyone else want to make any final closing remarks before we move on to our next panel? Well, thank you all to each of you. This was very inspiring, a lot of fun for me. So I want to thank you all for your contributions today. Thank you. All right, so now we're on to our third and final panel for this symposium on grand challenges. This panel considers cultural, structural, and educational issues. I am so pleased that Nancy Grimm, the Virginia M. Ullman Professor of Ecology at Arizona State University, has graciously agreed to be the moderator, and I'll let Nancy go ahead and introduce her panel.
Thank you, Marcia. It's a real pleasure to be part of this really interesting symposium. And I want to thank the previous panels for laying the groundwork on how grand challenges might be identified and developed, and for some excellent ideas about what those grand challenges ought to be. And the Q&A that we just heard, it leads us nicely into this final panel. The purpose of this final panel is to explore in more detail what the process of developing grand challenges might look like, how to ensure that it's societally relevant, ethical, and inclusive, what the consequences might be for our educational system and our research modes, how the intended outcomes might go awry and what we can do to prevent that, and the overall impacts on our society and on the Earth system. So, as Marcia said, I'm Nancy Grimm. I'm a professor at Arizona State University. My own personal interest in this topic is a conviction that we need to transform the way that we train our graduate students in light of the grand challenges of the Anthropocene, As a professor at ASU for the past 40 years, I feel fortunate to be in a place that values an inclusive education and nurtures interdisciplinarity, and a university giving back to the community of which it's part. But I think in the face of these grand challenges, we all need to rethink the way we educate graduate students and in the process, learn new modes of doing research ourselves. We need to welcome students from all backgrounds and train them in collaboration and team science, interdisciplinary and systems thinking, understanding issues of justice, equity, diversity, and inclusion, communicating their science in new ways, and focusing on solutions. The problems that need to be solved, the grand challenges for our Earth system, are going to create new roles, and our students must be ready and actually are increasingly motivated, we're seeing, to fill those roles. So I think this issue of a transformative and inclusive education is one of the issues we'll be talking about here. And it's going to be addressed from a broader perspective by our first panelist, Lori Leshin, who is president of the Worcester Polytechnic Institute. Lori is a space scientist who's been at WPI since 2014. She's contributed great thinking about convergence and problem-based teaching. Second, I'm going to introduce all the panelists first, and then we'll take it away. Second, we have C.K. Gonzalez, who is the director of the Center for Professional and Research Ethics at the University of Illinois and an expert in leadership and ethics. C.K. will touch on how to cultivate and maintain cultures of excellence in science, lessons that the National Academy can use to ensure inclusion and trust in the process of developing the grand challenges. She also has some comments on this process in the context of the current pandemic. And then finally, we'll hear from the National Academy's Foreign Secretary, John Hildebrand, who is a research professor at the Regents professor, at the University of Arizona and a neurobiologist. John has been Foreign Secretary since 2014, and he'll bring into our discussion issues of how we can learn from, contribute to, and work with other countries in developing or implementing the grand challenges. So at this point, I'd like to turn the floor over to our first panelist, Lori Leshin, to begin the discussion. Lori?
Thank you, Nancy. And it's a pleasure to be here. I hope all watching and listening are safe and well. And many thanks to Marcia and the academies for this opportunity to contribute to this really timely and exciting topic. I tend to think of this panel as the yes-if panel. We are saying yes, grand challenges in science are a great idea and can be successful if, and so here's one big if, so big that it was extensively discussed in the last panel, if we're able to dramatically advance convergent science that crosses traditional boundaries, whether they're between disciplines across the sciences themselves, between the sciences and humanities or other disciplines, or between scientists and the people and communities who are impacted by the grand challenges that we seek to address. So in order to meet the opportunity ahead, we need to focus on key actions that will enable convergent science to thrive. And I propose that among the two most important shifts that we will need to make are in how we educate scientists and how we reward them. So first, education, and Nancy already mentioned this, I'm talking about significant shifts in both undergraduate and graduate education, shifts to engage students much earlier in the experience of working in large, highly diverse teams, in addressing real world problems rather than just homework problems. At my institution, WPI, our motto is theory and practice. So Pam Matson's comments set us up very well for this conversation. We are a pioneer in project-based education and learning in STEM. 100% of WPI students experience multiple major projects during their education. Those are projects within their STEM fields, projects that replace traditional general education requirements, and importantly, projects aimed at solving specific community-based problems that sit at the intersection of technology and society. And our students do so, especially in that last case, solving those societal challenges. They do so while embedded in over 50 communities in 31 countries around the world as part of their educational experience. And we have research studies associated with this open-ended project-based work after many years of doing it, and in many cases, many years after the students have experienced it. And without going into a ton of detail in the short time I have, the students do find that it shapes both their professional and personal values, that it dramatically increases their ability to work across boundaries. And also, and as a college president, this is my favorite thing actually about it, is it makes them realize, it makes learners realize that they need to take responsibility for their own learning, which is so critical in the fast-moving world of convergent science and technology. And lately, and we can maybe talk more about this in the Q&A, but we've been focused on ensuring that students learn the skills to emphasize inclusion on their teams, to ensure that project work that they're doing is done equitably. So again, on education, I suggest that much more real-world, hands-on, transdisciplinary, and community-embedded project work will be needed at both the undergraduate and graduate levels to train the next generation of grand challenge-oriented scientists. Next, I want to turn my attention for just a couple of minutes to the reward systems of science. And here the issue is one for professional scientists, especially STEM faculty. The truth is that although we all might say that we value work on applied and community-based scholarship and transdisciplinary scholarship, most of us work within a system that explicitly does not value it. Said another way, the traditional incentive systems are currently misaligned with the values of science in the era of grand challenges. So this past October, I had the privilege of chairing a convocation at the academies on re-envisioning promotion and advancement for STEM faculty to begin a national data-driven conversation about STEM faculty advancement. The proceedings of that convocation are available on the Academy's website, and we're working towards convening, hopefully, a consensus study on this important topic. At WPI back here locally, we have recently overhauled our promotion criteria to be much more inclusive of convergent scholarship. And importantly, it's still scholarship that needs to be disseminated and be able to be evaluated. So not only do our updated criteria better align with our institutional values around meeting societal needs, last year they resulted, for the first time in the 150-year history of WPI, a STEM institution, last year they resulted in more women than men being promoted to full professor. So I just want to close with one reflective comment on this moment. Institutions of higher education have long been considered to be such slow movers that there are jokes about them being places where glaciers go for a relaxing vacation. But in this moment, I think it's a really important thing to remember that our institutions pivoted exceptionally quickly and effectively to dramatically change our entire operations in the face of the COVID-19 pandemic. So let's not be deterred in this moment by fears about change. We can change education and we can change reward systems. And in fact, we must change them should we hope to succeed in solving grand challenges in science. Thanks, Nancy. Back to you.
Thank you very much. That was excellent, Lori. As I said, we'll be saving our questions and answers until we've heard from all the speakers. So now we're going to be hearing from CK Gonzalez. Take it away.
Thank you. I think my remarks build directly on Lori's because, and all of the symposium so far, actually, because one of the things about the grand challenges is that in order for people to be comfortable and trust what scientists, the experts, are doing, there has to be a foundation of trustworthiness. And I think the Academy under Marsha's leadership has thought a lot about the trustworthiness of science. And in order to communicate trustworthiness, you have to be trustworthy. Underlying that has to do with reinforcing the cultures of excellence that we talk about a lot. Culture is how people behave, and I think that it is amenable, as Laurie just mentioned, to change. And I think that we have learned so much in recent years about improving inclusivity, about cultures of excellence, about improving internal integrity. And those are things that I think underlie a successful set of grand challenges. Our premise is that cultures of excellence are about more than what is done, it's about how it's done. So with rigor, with reproducibility, with inclusion, with integrity. And a lot of that has to do with starting at the most basic level in the research groups and how we select and include people, who's included at the table, whose voices are heard, who's meaningfully at the table. How much are people when they're there heard? because groups don't always produce data and results. Research groups sustain themselves as ongoing parts of the enterprise, and they build and contribute to the talent pool. If you look at our current system and the current moment that we're in, this is a moment both to stop and reflect about how our institutions are working and how they could work, because we face massive challenges in our institutions. We are going to have, there will probably be, if you guess, an infusion of some stimulus money in some ways for science. Beyond that, though, a lot of our institutions are going to be extremely challenged financially, and we're going to be extremely challenged in terms of who the talent pool, the demographics and change in our talent pool. The body of our students coming in will be changing, both in size and composition. And all of this is happening in this complex system where a lot of players interact. And this is a diagram out of the Fostering Integrity and Research System, where we have a lot of players interacting all the time. And it's a global system. And these systems, each of these pieces, interact with each other and their stresses. And we are going into a time where this complex adaptive system is going to be stressed, and all of the places that we already have structural flaws and concerns are going to be in a situation where those flaws are amplified. And I think that we have to start thinking about, are we going to double down and entrench into how we've always done it, or are we going to think big thoughts internally as well about how we move forward? So it raises some questions for us. Who will have a seat at the table and be able to have a meaningful voice as a scientist who enters the system and participates in the system, and about the science that's going to affect every being on the planet as we do it? How will we make choices in shaping the environments that emerge after this in terms of incentives, rewards, the competition, the pressures, the selection, evaluation, some of the issues that Lori just raised? And we're in a sort of moment of pause. Institutional leaders are scrambling as fast as they can to look at alternative possible futures and how their institutions are going to shape. Individual scientists, many people have their research on pause, have had to close down their labs at real cost, and are looking at very long startup phases, some of them, for when the world finally does restart. So in this time of pause, if you're not one of those people who is scrambling as fast as you can about either your institution or working on virus-related research, here are some questions that I would pose to you. Is that uncertainty, fear, anxieties, insecurities are going to be rampant among those with whom we work on our teams going forward. How good are your skills at difficult conversations? How comfortable are you going to be at helping particularly the early career scientists, whether they're students, whether they're grad students, whether they're postdocs, whether they're people who are on the tenure track now, at addressing the very real future challenges that they face, regardless of the need that we have for all of their talent? Their career prospects are really at risk in these moments, and we need to have the skills and the tools for helping them build careers and address those anxieties and uncertainties. This is a moment for working on those skills. There's a lot of information out there, and if we're asking everybody to take their education online, some of us could do that too, because there's things out there for improving how we hold difficult conversations and how well we listen. Because you have to have conversations not only about facts, we also have to deal with the feelings, and uncertainty will ramp up all the fear and uncertainty out there. As we move forward as our institutions, how will we strategize to emerge stronger and better and more aligned with our values and the missions of science? The Fostering Integrity Report went back to the core values of science and came up with 6: objectivity, fairness, honesty, accountability, openness, and stewardship. Why are we doing what we're doing, and do our systems actually advance those core values, and how do we do better? So the questions I would leave are, How will we include diverse perspectives and voices in shaping the future? And how will we measure the contributions of individuals, of collaborators? Because our current system doesn't do well with indices of collaboration. And I'd just like to say thank you to the Howard Hughes Medical Institute, who's working with us on a leadership development program that they call Labs That Work for Everyone. And we're really interested in how do we support leadership development among all scientists across all career levels to lead us into the grand challenges we all need for this world to prosper. Thank you.
Thank you so much, Tina. That was really outstanding food for thought and a nice build upon what Lori talked about as well. So now we're going to sort of move over to sort of more international context. John, the floor is yours.
Well, thank you. It's a real pleasure to be the caboose on this whole symposium. I'm, I guess, the last scheduled speaker. Let me start by saying that it strikes me that all grand challenges are global. Any grand challenge in science that we, the National Academy of Sciences, might choose to address, progress is necessarily going to depend on international cooperation and collaboration. And at the same time, interference with free flow of people, ideas, technical advances, or discoveries is going to be harmful to that progress. So that naturally brings us into considerations of governmental policy implications, politics, and all of that causes me to focus, as Chuck Mansky urged us to do, on social sciences. It's easy for us all who are physical and biological and medical scientists to forget how important the social sciences are. And so I think the only way we will achieve real progress in addressing global challenges is to understand the important role of the social and behavioral scientists to help us understand why people and governments behave the way they do and how we can progress beyond the limitations that are imposed by that behavior. Now, I also want to say that our best bet in achieving progress on grand challenges is to build and strengthen and sustain institutions and mechanisms for international cooperation, collaboration, communication, and public engagement in science and research. It's a big order, but there are means by which we can make progress with that. And I'm going to cite just one example that's very important to our National Academy of Sciences. And that's a consortium of essentially all of the academies of sciences and medicine in the world. This is the Inter-Academy Partnership with more than 140 participating academies, member academies. This organization has a focus on basic science, on medical and health science, on policy, science for policy and policy for science. And it brings people to the table from every corner of the world. I think this is essential if we're going to make progress on grand challenges of any kind, but certainly the kind that we're discussing here. Individual academies bring evidence-based advice to their governments. They typically operate with a great deal of independence from political forces, even if they were created by political and governmental agencies. And they equip governments with the knowledge and advice necessary to make intelligent decisions about support for and encouragement about and education in science, technology, and engineering, mathematics, medicine, you have it. So I want to encourage all of you anyone who doesn't know about the IAP, the Inter-Academy Partnership, to look it up and read up on it. It's really an amazing organization, and our academy our three academies actually have very important roles that I wish I had time to describe. Another organization I want to mention only very briefly, but it's very important and growing in importance, is the International Science Council, or ISC. Again, you can read about that online. That is an organization that brings together many academies of sciences, but also disciplinary unions in physical and life sciences, and at the same time brings a large number of social sciences organizations to the table. So that is that organization very robustly engages social and behavioral sciences. And it, therefore, in my view, it has a very important and promising role to play going forward. I want to just say a positive word about the educational advice that we got from Lori. I feel very strongly that we need to rethink education overall, but especially relating to STEM fields going forward. And I mean not just graduate students. I mean from kindergarten all the way on. We need population in this world today that understands a bit about how science is done, what the uncertainties of science are, and to engender respect for and interest in science among all the population. I think we in this country don't do a good job of educating the population in general about science and related areas. And I think there are countries in the world that can teach us a lot about how to do better. So I want to call attention to that. Finally, one grand challenge that's close to my heart and that hasn't been mentioned yet is the importance of biodiversity on planet Earth. It's staggering to consider how many species of organisms haven't been described yet, and that we're losing by the millions every year through extinction. So I just want to add that to the list of wonderful candidates. The challenge there is to assess and describe the importance of and preserve the Earth's biodiversity. And I think this is also an area that has global reach and needs global cooperation. Thanks.
Thank you so much, John. So I have a couple of questions that I want to put to specific ones of you, and then the others can weigh in. I'll start with something that John started. Lori, you said a little bit about WPI's project-based learning program, and it seems to be a good model for engaging student scholars in grand challenge type questions. Thinking about some of the issues that we've brought up, for instance, about having inclusion in the grand challenges, do you see any potential pitfalls in using grand challenges as a basis for STEM education at the undergraduate level, the graduate level, and indeed, as John has mentioned, at the K-12 level?
Honestly, I don't see a lot of pitfalls. I do see some challenges, and they're probably mostly on the part of making sure our faculty colleagues are comfortable operating in a space that's somewhat different, probably quite different than they normally do. I think, in fact, it's essential that we begin to pivot science education to be more grand challenge driven. And the reason I say that is that we see the results when we do. We see the results in terms of building a more inclusive scientific workforce. Al Romig talked about this with the Grand Challenges in Engineering, their Grand Challenge Scholars Program. And I can say, as someone who's a part of that program here at WPI, almost all of our Grand Challenges in Engineering scholars are women. It's really quite something to see how framing these questions from the perspective of grand societal challenges or even grand scientific challenges really do draw people in across much more diversely. On the K-12 question, just for a moment, I am going to stick to my love of project-based learning here and say that I think that's also a key way that we can begin to transform K-12 STEM education. There are some great organizations doing it, like Project Lead the Way has wonderful project-based K-12 STEM programs. We train all the teachers in Massachusetts who deliver those programs, and I can again say that they are extraordinary. Things like FIRST Robotics, that's a problem-driven approach to teaching and learning STEM, engages people who otherwise would not pay nearly as close attention to their science and math education. So I think there's great opportunity here to expand this way of teaching and learning, but it does take support and training for the teachers at K-12, the faculty at in higher education. And so we would have to put into place the support infrastructure there for development of great teachers and great faculty.
Yeah, we do need to value our teachers a little bit more than we do now, I think.
What a concept.
CK, I have a question for you. Can you talk about the ways that might sort of come from your experience in building teams that if the NIS goes ahead with building these grand challenges, what are some of the tools we might use to communicate with and bring in diverse voices into this process of developing grand challenges? I mean, we could all go into the ivory tower and just start talking about what we think is cool, but I think some of the things you've said, it's really important to be hearing from diverse voices. So what are some of the mechanisms we might be able to use?
I think the mechanisms are pretty consistent across human interaction, and some of the early speakers talked about the challenges of interdisciplinary collaboration and how when you collaborate with colleagues across disciplines, you often need to learn a new vocabulary and learn to listen very carefully. Listening and asking questions are at the foundation. I think for scientists and, if I may, members of the academies who are respected and at often career peaks and respected experts, I think it's really important to acknowledge that you hold power in these conversations. People in academia are often not very comfortable acknowledging or even understanding that you hold power, because people in academia tend to feel powerless, even though as you ascend, you acquire more and more power, and you don't often acknowledge or understand the effects of that power on others with whom you speak. So I think understanding and acknowledging the fact that disciplinary expertise doesn't necessarily give you human expertise. We have a lot of colleagues in social sciences and people who do all kinds of research in communities who have expertise to share. I think it starts with understanding that we can't go in and say, we're the experts, we're here to help you. We have to actually listen to people and ask them questions and find out and invite them to participate and give credence to the things they say, and not say, oh, no, that's not right, and dismiss them, which I see happen probably more than is good for our community. So I think fundamental listening and asking questions, and kind of listening that you really process through your brain, not the kind where you say, oh, yeah, now how soon can I talk? The kind where you actually, in the negotiation literature, we call it cultivating curiosity. People are endlessly fascinating. And if we ask questions with a real curiosity, you can learn wonderful, important things that shape where you go.
Super. Anybody else want to follow up on that, or have an idea that you want to put out there for? This is a chance to sort of influence how the process might actually happen if we get it started. So,
I guess I would add, I think there are beginning to be some really good examples, especially in the public health fields, of great partnerships between scientists and communities. There are things like the Thriving Earth Exchange that the American Geophysical Union has stood up, where we're working to connect communities with scientists and funders. I was involved in the founding of that. It's gone way further than when we were there at the beginning. Mm-hmm. And places where scientists can not only contribute their habits of mind and ways of thinking and expertise, but also can learn how to approach these problems differently and engage those whom the solutions will most impact in the creation of those solutions.
Yeah, I'd like to chime in too. In a year or two ago, when France hosted the G7 Economic Summit, there was a science component, as there is every year. And one of the topics that they raised and for which a statement was developed, an advisory statement, was on citizen science. The idea that we have to get past the long-standing tradition of them and us, that we're in the ivory tower, we know more than everybody else. Mm-hmm. In fact, we will thrive going forward only if the public and the people who represent the public in leadership of governments understand how science is done, why it's important. And in order to do that, it's the more people we can engage, the better. And I think engagement has to start with little kids. Every kid is a born scientist. All you have to do is watch any child and you realize that. And we scare it out of them by the time they're teenagers. We have to stop doing that. We have to engage them and keep them engaged. And finally, I would also advocate for active problem-oriented education. Here at my university down in Tucson, the other big university in Arizona, we are in the middle of a revolution of converting lecture halls into active learning spaces and basically abandoning the old tradition of lectures, trying to fill empty vessels with facts. We have had enormous success with over 100 faculty now teaching through this active learning, group-oriented, problem-solving kind of approach, and it's been brilliantly successful. Anybody who thinks that you can't get faculty to do that hasn't even looked into how it's done. The fact is we can't make room for enough faculty who want to do it.
I think that's a great point, John. And I just want to say that one of the pushbacks we often hear on the project-based learning is like, oh, well, you're a relatively small private, STEM institution. We have 5,000 undergraduates, so we're not that small, but we're not U of A or ASU size. Well, nobody's ASU size, but still. But I'm thrilled to hear you're proving that you can do this at scale. Absolutely.
I think it's happening in a lot of large universities that it is very impressive. John, I want to follow up on some of your comments about the international groups, and you did mention the IAP, the Inter-Academy Partnership, and the International Science Council. There's also quite a lot of activity going on relevant to the UN and groups in the UN and so forth, and also individual countries that may have done this sort of exercise themselves, the Grand Challenges exercises. And then the SDGs, which when we met before, I think you commented that, the SDGs ought to be the Grand Challenges. And we've heard that 3 times today. So can you, you already answered the question of how global these Grand Challenges need to be, but should we include representatives from other nations in the process of developing the Grand Challenges? How can we benefit from the things that have already been done internationally in this sense?
Yeah, well, there's a lot to say about that, but I did mention the SDGs only because it was so nicely mentioned in several other presentations. I think the SDGs and the Grand Challenges for Engineering, I love both of those. They are great organizing principles for going forward. But to your specific question, we in the National Academy of Sciences have a wonderful way we could do just what you are asking about. We have international members. These are leading scientists in all areas of science around the world who are elected to what used to be called foreign associate status, and we're about to change that on Monday, I'm pretty sure, to international members. And these are people who we want to engage ever more in the work of the Academy. In the past, it was sort of an honorific thing, and they didn't have much of a role to play. I'm determined that we're going to change that and really engage those valuable colleagues. And it's a wonderful way to find out what's being done in other countries. I could mention so many examples, but just in the midst of this COVID-19 pandemic, in Senegal, there's a leading laboratory for vaccinology and virology. Who knew that in Senegal there is that? And we have a foreign member, an international member in Senegal. We can learn from what's being done in places like that that we might not otherwise have any knowledge about, simply by engaging our international members more robustly. So thanks for asking that.
Super. That's great. Thank you. I just wondered if anyone, you mentioned it a little bit, the pandemic, but Dr. Gonzalez talked about how we can ensure inclusion in developing the Grand Challenges, especially in light of this pandemic that we're experiencing right now. So what do you, I don't know if there's a crystal ball you can reflect on how the educational system might need to change in response to the aftermath, the pandemic and its aftermath, if there is such a thing. Anybody want to take that question up? We had a long discussion about it when we met earlier.
Yeah, I literally just wrote to my former board chair saying, I wish I had a crystal ball, could look back 24 months from now and see exactly how that was going to happen. I don't think any of us can see with clarity what's going to happen next month, much less longer term. But I do think there's going to be some really interesting opportunities, and that I think it's important that we don't only focus on the near-term recovery, that we do really think hard about how the system could have changed and evolved. in some ways, I think of this like a Sputnik moment. Back when Sputnik went overhead, it scared the heck out of Americans. It was a very different situation, obviously, a much more short-lived sort of jolt to the system. But it changed education. Most of the foundations for STEM education that we have today were built literally through things that came after the Sputnik, after Sputnik happened. And we are in a similar kind of moment, and I think we have to wait and see how that will evolve. But it is a moment to seize the opportunity for the kinds of changes we've been talking about in this panel.
So I'm prompted just to point out that for this country and others in the world, the barrier to taking what we know is coming, and the pandemic is a good example, and to have us prepare for it. The barrier to that is political. And this gets back to human behavior and social science. We have so much to offer, we, the STEM enterprise globally, and yet there are such barriers to absorbing and respecting and taking advantage of what we can offer in this country, unfortunately, and in many other countries. We have to address that. That, to my mind, is maybe the biggest of all grand challenges, except maybe finding life in the universe.
It's interesting because we have a question that came in from the audience. That's I don't know if anybody's going to want to take this one on, but it reflects on what you just said, John. The question is, the scope and optimism of the thoughts presented are excellent, but are we consigned by our biology and education to have war? I'm not sure that anybody wants to take that on, but it does speak to the sort of idea that maybe personally, I think we're all optimists, and we don't believe that there's that we're stuck. We can find a way out of this.
I would hope that we could transcend our biology. I mean, I'm afraid our biology may actually equip us with some tendencies to xenophobia, but I would like to think that because we have big brains, that we could transcend those biological limitations and learn from terrible mistakes of the past. Again, there are barriers to those messages, but I'm very hopeful.
Thanks, John. I have one more question I'd like to ask of CK, and it's stemming from some of the things we talked about also earlier. The potential pitfalls of developing grand challenges, of actually the NAS moving forward to develop grand challenges from the perspective of ethics or inclusion, and how can we ensure that we avoid those pitfalls?
I think we have to start thinking again individually, which is one of the things that we talk about when we do our leadership development and work with particularly early career scientists is what we call the career tragedies, an acronym: temptation, rationalization, ambition, group and authority pressure, entitlement, deception, incrementalism, embarrassment, stupid systems.
I love it.
It's our job to manage ourselves and be aware of when we are acting on cognitive biases. We have to educate ourselves, and we have to recognize what it feels like when we are tempted to cut a corner, tempted to just smooth the curve just a little bit, throw out that outlier, just, rationalize it away. You know what it feels like. I mean, the rationalization feels like, well, it's only one more cookie and I'm standing up anyway, and it was broken. We all know what it feels like, and we need to own those. And then we need individually, and then we need to own them organizationally, and then we need to organize them as we go through this process together. Because it is about being humble and being aware, and also thinking a lot about the really stupid systems that all of us have created. And one of my favorite articles is by Steve Kerr, and it talks about on the folly of rewarding A while hoping for B. We have a whole lot of folly in our systems, and it's time for us to own those and think about them. If we're going to try to do better when we come out of this, let's own our own pieces first.
Hear, hear.
Well, on that note, I think that's great advice, and I hope this has certainly been fascinating for me, and I really appreciate your thoughts, and turn it back to Marcia to end.
And I just want to add my thanks to it's been a great panel. Couldn't have asked for a better note to end on than your great advice to everyone, Dina, that really the rules of the road are within our own power to set. And anytime we set up a reward system that is counterproductive to the behavior we want to see, then shame on us. So with that, thank you all very much. And thank you for everyone who tuned in. More to come on this important topic. Thank you again.